Hi, welcome to the last session using R to do Bayesian subnational estimation with complex survey data. So this is actually the last of the 3 lectures that I'm giving, where we look at the codes and implement the methods for subnational estimates, and mostly for U5MR in this course. And in this lecture, we will be looking at a case study where we actually implement the methods and calculate U5MR using the latest Kenya DHS survey from 2014. Okay, so as like any real data analysis, the codes in this lecture are going to be a little bit messier because we're dealing with real data. We're no longer loading the pre-cleaned version of the data or example data sets from DHS directly. So there'll be a bit more codes to clean up the data, make sure things match each other. And again, as always, there's the HTML file online that lists all of the steps that we did in processing the data. So just to get started, as a quick overview of this session, so we will look at this, as I said, the DHS survey from 2014 from Kenya, and there's a URL to the DHS website. So for this particular data set, or actually for any real DHS data set, if you want to use the data set, you need to register with the DHS program. And if it's for academic purpose, they can typically give you access to the data within a day or 2. So for this analysis, we need to go to this website. Of course, you need to register with DHS for using the Kenya data. And then we need the birth records as well as the GPS data for the cluster locations. So we'll use the GPS data to basically map the clusters that we have in the data sets to the county level map of Kenya. And if you have followed the previous lectures already, you probably already have downloaded the Kenya map from the DHS spatial data repository. The link is again provided on the slides. And for that, the boundary shapefile, you don't need any registration. You can just go on there, and you should have the option to download both the province level as well as the county level maps from these websites. Okay, so assuming you have already got this data set, or you might be working with your own data set and have prepared the data to something similar in these formats. So as an overview of the models, so in this lecture, the target that we're going to be focusing on here is to estimate the yearly U5MR from 1985 to 2014. So this data set, the survey was collected in 2014 for our case in Kenya. So that's our time frame. And we also want to make projections up to 2019. And we'll only be using this one DHS survey. So we won't be doing using multiple surveys like I already showed you in the previous lecture, just to keep things a little bit easier. And we'll fit 2 types of models. The first model we have already looked at and actually fitted in the previous lecture is the smooth direct modeling. So basically, you calculate the direct estimates, and then you smooth the direct estimates using the methods we already discussed. And then we're going to also show the second type of model, which is on the cluster level modeling. So in this model, we will fit a binomial model on cluster level data directly. So we'll not do so the estimates will not come directly from the direct estimates. And as we will see, that this gives us more advantages when we have sparse data, especially if you're working with finer geographic boundaries as well as smaller time frame. Okay, and then of course we will, at the end of this lecture, we'll compare all of those estimates and some of the other things which we haven't really talked too much about in previous lectures. We will also fit the reduced form of both models. So we get the national estimates. So we basically remove the spatial parts of the modeling framework and then fit both models to get the national estimates, and then we will also discuss how can we potentially perform bias adjustments. So assuming if you have some information about how the estimated U5M are biased, we'll discuss how do we actually implement those in codes to perform the adjustments. We'll also talk a little bit more about how do we examine the model components. So how do we extract the posterior distribution of the random effects, and of course visually plot them on the map or as a time series, and then examine the model outputs from those diagnostic plots. And just to give you a preview of some of the results, so this is the first, probably not the last typo, the preview of the results, not the previous. So this is the direct estimates that I'm plotting out here. So remember the target here we're working on is to get yearly estimates of U5MR. So this is some of the selected years, because there are 35 years in this period. I'm just going to show you from 1985, 1990, 95 up to 2014. So those are the direct estimates by just using the data without any smoothing. And as we have shown before, that the hatching here represents the uncertainty. So the uncertainty is measured in this plot as the width of the credible interval for the direct, 95% credible interval for the direct estimates in this case. So you can see the width of the uncertainty, the confidence interval goes from 0 to 100 up to very large 800 to 900. So again, they're measured as the rates per 1,000 light bursts. So you can see that a lot of the hatching lines here are very narrow, especially if you go to early periods. You can see there are a lot of uncertainties here, which is not surprising. And there are a lot of the places where it's completely grayed out, which corresponds to the places places and years where we don't have any data, or actually we don't have any depth in those areas in that particular year. And then we will also look at the smooth direct estimates. So basically taking the results on the previous slides, and now we can fit a smoothing model on top of it. And if you compare the two, notice that the color scale in those two figures are not exactly correspond to each other, but uncertainty bands have the same interpretation. You go from direct estimates to the smooth direct estimates. There are a lot of the places, like here, if you're looking at 1995, in this region, this is direct, this is smooth direct. You can see that we reduce the uncertainties by quite a bit by smoothing the estimates across space and time. And of course, we don't have any areas that are completely grayed out, because we can use the neighboring areas and the neighboring time periods to borrow information to estimate those U5MR rates. And this is the results on the cluster level model. And again, the color scale is different, but the uncertainty is similar. It's defined the same way. And we'll compare the results more closely at the end, but just again to illustrate some of the places, like for some of the places like here in the direct estimates where we really don't have a lot of data, so the smooth version depends on the time trends going back in time, mostly. And once we start modeling on the cluster level, it really doesn't matter that we don't have a depth, because we still have some information there, and we can hopefully get better estimates for some of those situations. Okay, so this is basically, by the end of this lecture, the things that we'll be looking at and compare. And just some of the learning objectives here. So of course, I want to show you a complete workflow of estimating U5MR, starting from the beginning to getting the results, and some of the intermediate considerations like bias adjustments, and in particular, one thing we'll discuss is benchmarking to using the national models. And then I want to use some of these more complicated examples to highlight the function arguments, how to specify different models, what are the considerations, and then how to make the most out of the output of the summary package. Of course, we will, as I said before, we will use visualizations like we have just seen to evaluate and interpret the fitted models. Okay, there's a website to all of the materials. And at the end of this PDF slides, there are additional resources. So the smooth direct estimates are mostly discussing these first two papers. And the binomial model, the cluster level model, was discussed a little bit in this 2018 paper as well. And of course, if you go to the CRAN website, the CRAN site of the summer package, there are more documentations and explanations in how to fit this kind of model. So with that, I will switch to RStudio and see things in real action. Okay, so this is the RStudio, the familiar RStudio that we have looked at in the previous lectures. So up here, I'm pulling out the HTML file that you will be seeing on the website. So for this lecture, because some of the methods, some of the models are actually very computationally intensive to fit, I have already fitted some of the models and loaded in the workspace, as you can see from here, so that you don't have to stare at me and the screen for hours just to get the readouts. So for this part of the lecture, I will first go through some of the steps in preparing the data, and I will talk and actually fit the smooth direct estimation, the smooth direct modelings in RStudio. And then for the model-based estimates, it will take a much longer time to run, and we will then switch to the HTML file where we can look at some of the model outputs and compare the results. And the HTML file also gives us better flexibility in zooming in on the plots, so it's better for the presentation as well. Okay, so with that, I will start with the workflow of estimating subnational estimates of U5MR. So of course, again, the first thing we do is to load some of the libraries or the packages. So for this lecture, we will be using the summer package, the ggplots, and the Greek extra for presentation. Okay, so reading the data. Reading the data should be very similar to the things that we have discussed in our first lecture. So here I have downloaded the DHS birth record files for this particular Kenya survey, the 2014 DHS survey. So I'm going to use this RIS-data 13, and I specified the file name. I'm going to read this to load the full birth records, the full birth history to my workspace. Okay. So this will take a few seconds to finish reading them. And after the birth records have been read into R, I will then reading the maps. And for the purpose of this demonstration, I will actually reading two maps, one for the province level province level boundaries of Kenya. So there will be 8 former provinces. And then I will also reading the county level map, which contains 47 regions in this DHS survey. We'll actually merge these two later so that we have a understanding of which county belongs to which province, and then we can use some of the additional source of information to help us combine the data in that way. Okay, so this birth file has been read into R. So now we're going to read in the map using the rgdelfun package. And then I created 2 shapefiles, one called geo0, which corresponds to the province level boundaries, and then this familiar geo and AMAT corresponds to the county level maps. And you can see from here that AMAT is a matrix of 47 rows and 47 columns. Okay. All right. So the first thing we are going to do is to get the smooth direct estimates So in order to do that, we need to follow some of the recipes we already discussed before, which basically turns your data set into a person-month format, so you can use discrete survival modeling to calculate the U5MRs, the design-based U5MRs. But before we do that, remember, as I said before, that since we're working with real data, a lot of times we need to examine whether or not our data contains all the information we want, whether there are missing information, there are elements missing, or things like that. So the first thing here, what I'm doing is to load the shapefiles for the clusters, so basically where each of the clusters are. And I will examine its longitude and latitude to see whether or not all the clusters are actually assigned a particular, in this case, counties. In other data analysis, depending on the level of inference you want to perform, whether or not the cluster is assigned a particular admin 1 or admin 2 regions. Okay, so this few lines of code that looks a little bit long, but it's really simple. It's basically taking out the cluster IDs, longitude, latitudes, and then I'm using this map points function to map those GPS locations into a particular shapefile. So I repeated this for geo and geo0, and I created a new variable called region and a province. And then I merged these two data sets together using this line of commands. And you can see that there are 9 regions. There are 9 rows in the GPS dataset that doesn't really have a region assigned to it. And you can go in there and examine those 9 rows, and you'll find that those are the clusters that assigns a longitude and latitude to be 0, 0, which doesn't really fit into the where Kenya is. So this kind of things might come up in other data sources as well, and usually when this happens, you need to manually go into the dataset and try to figure out where those clusters actually are, if there's such information available. For the purpose of the demonstration, I will just do the simple but not exactly right thing, which is just delete those unknown classes so that we don't spend too much time on this step of data processing. Okay, so now I have deleted those classes, and I will subset my person-month records, so I'm only using the remaining classes when I fit this model. Okay. And now this line of codes basically merge my person-month files, this birth variable that we created, and merge it with the GPS locations, so that for each person month, we have not only a region variable which corresponds to the counties, but also the province which corresponds to which province the clusters lives in. Okay, and I will rename this column V023 to the one that we just created. Okay, so now that our data have been processed, we will use this function to get the person months. So the function getBirth, we have looked at it before. And if you look at the document of getBirth, you see that there are a lot of customizations that can go in there, and we have briefly looked at some of those before, such as how to cut the age groups, that's a month cuts, and how to cut the years, that's a year cuts, so that your output person months will have a column that corresponds to the age groups as well as the periods. So in this case, we will keep this default age group, so this 6 age groups that we have been using throughout this lecture series. And now I'm going to use define this year.cuts arguments and calculate yearly estimates. So the periods here we're talking about are basically from 1985 to 2019, and every year gets its own periods. Okay, so there are additional things which are default to be the corresponding to the latest DHS recode manual, but if you have a different data set, you might want to change some of those things as well. So just for simplicity here, we will now specify the rest of the arguments and just take them as defaults. And run this line, which will give us the person months file that we have been talking about. And then once we have the data, I will rename it a little bit so that things like V024 going to be renamed as region, and V001 is a cluster ID, V002 is the household ID, et cetera, et cetera. So just so that's one way go down to the rest of the modeling part, this will be a little bit more informative to look at. And of course, just like before, I will extract this variable that's called years, which is basically the levels of the different time periods. And in this case, it will be the year numbers from 1985 to 2019. Okay, so this step is down. So let's reformat our data a little bit, take out this variable, and we can take a look at our data sets. And you can see exactly this looks like a person months format. And with a little bit smaller number of columns as before, because we don't really need that many for fitting the models. And you can look at the years variable, which gives you the names of the years that we've been feeding into the model. Okay, so if you work with a period model where you combine data from multiple years, this years variable will give you things like 1985 to 1990. Okay. So of course you can specify the months cut to get other in order to calculate other mortality estimates as well. So you can, for example, organize your data so you only take out for the infant mortality, you only take out months from 0 to 1 and 1 to 12, which I will not discuss, but there are possibilities to customize the functions for doing other things as well. Okay, so now we have the person months. I'm going to use this function to calculate the direct estimates. So just as we have looked at in both of the previous lectures, I need to specify a few different things. The birth data, which is the one that we just created. The years variable, again, these yearly labels that we just created here. And then I need to specify which variable corresponds to region, which corresponds to age, and which corresponds to time, of course, and then some of the other sampling design variables such as clusters and weights and strata. Okay, so again, you can look at the documentation of getDirect, and some of the common arguments are already built in, so you don't need to specify all of them if they're in the standard format you just get from the previous functions. Okay, so I have actually already run this line of codes because it will take a little bit of time to calculate the direct estimates because you need to loop through all the combinations of the areas and the times. And I have already done that, load into R before we started. So you can look at the estimates. So this is what you should get by running this line of codes. So you have the direct estimates, again, starting from the national estimates. And years here corresponds to each of the yearly periods. And then you have the estimates, lower and upper values, as well as on the logit scale, the estimates, variances, and the precisions. And after the national models, going down there, the region becomes each of the 47 regions. And you can see that we have estimates up to 2014, and everything else following that will be NAs. Okay. And also, when you run this line of codes, and with this fine geographic and temporal resolution, it will pop out a lot of warnings that saying that a particular year and a particular region, there are no deaths in that combination. And as we will later see in more visually in the figures, that there are a lot of the combinations where we don't really have the direct estimates. And in that case, if we have a lot of those things, the smooth direct estimates might be thrown off by the lack of information there. Okay, so another topic that we haven't really covered in this lecture series is how to make adjustments. So the rationale for making adjustments is that sometimes we have additional information that tell us the direct estimates might be off by a certain at a certain direction. For example, so this is just one situation here, that in countries with high prevalence of HIV, the estimates of U5MR might be biased because women who had a high risk, HIV positive women had a higher risk of dying, and those women who had given birth were less likely to be included in the surveys, and then the children of the HIV positive women in turn are also more likely to have a higher probability of dying compared to those born to the HIV negative women. So basically, you might have an informative missingness, and if you can calculate from additional source of the data the scale of such bias, you can use that information to adjust your estimates within the summer. So here we consider the situation where we have the ratio of the reported U5MR or the calculated U5MR to the true U5MR. So if you're looking at the HTML file, there are a little bit more mathematical details about what the adjustment formula looks like. But basically, if you have this ratio, then intuitively you can scale up or scale up or down, depending on which direction it goes, your estimates by this ratio. So we have in the summer package as a demonstration a data set that's called Ken data, where we have exactly this bias adjustment ratio for the 2014 DHS survey. And you can look at this data frame. And it basically gives you, for each year and each region, and including the national estimates where the region is all, it has this ratio, which is what the reported U5MR to the true U5MR should look like. Okay. So we will use this adjustment data frame. And before we do that, we're going to make one small change here by changing the column, because remember that in this analysis we have been calling region. So the region is our primary unit of analysis. We have been using region to denote the 47 counties. And if you look at this adjustment data frame, so if you look at the last few rows, so you see it, you might realize that the region here corresponds to the provinces. So just to avoid any future confusion, I will rename this column to be province instead of region. Okay. So basically, if you have this by year and the province adjustment factor, you can use this get adjusted function in summer to recalculate your direct estimates, or actually other estimates as well. So it scales up or down your estimates, and then also change the variances, your confidence intervals, as well as on both the probability scale and on the logit scale. So here we will use a few lines of code to clean up the data a little bit. So here I'm basically adding another column called province in the direct estimates. So remember, our direct estimates were previously calculated on each of the counties. So here we're just putting back the province information by merging it with the GPS datasets. And then I will calculate the logits at the logit level, the confidence interval, by just taking the logits of the confidence intervals on the original scale. Just so that when we plot the results, we can more easily compare the results directly. So now I use this getAdjusted function. As I said, we need to specify the data and adjustment ratio, and then I need to specify the column names. So the column names needs to match between the data and adjustment ratio for the years of the province, for the years of the regions. So here I'm specifying the time variable to be the years, the region variable to be province, and then which column gives us the adjustment factor, which is the ratio column here. Okay, and then I specify the rest of the column names that corresponds to the things that we want to adjust, which are the lower and upper bounds of the estimates. And if you run this, it tell you how many estimates were adjusted following this line of codes. Okay, so now our adjustments our adjustments are done. So our estimates have been changed a little bit by the estimated bias ratio. So now we can fit our model. So again, first we will fit our national model with this one line of code. I'll set it run, and I will explain it a little bit more. Okay, so we'll fit this national model again using the fit_inla function. And again, because we're not fitting any spatial model, we'll need to set the geo and AMAT arguments to be null, and then we need to specify the years and the range of the years, what's random walk model that we want to fit. In this case, I fitted a random walk 2 model. And then I specified m equal to 1, which corresponds to, for each period, it corresponds to 1 year. So that's internally, it will recognize that this is not fitting a period model where we might have random walks defined on different scales than the periods themselves. Okay. And then we can use this getSmooth function, again using some of the similar arguments before, to get the smooth estimates from the national model here. Okay, since this is probably going to take a little bit longer time, and I have already calculated here, as I can see from my environment variable, I'll just skip this step already. Okay, so the reason we want to fit the national model are twofold. First of all, we might do something like this, where we just plot the national model. So I just do this plot out 0, and I need to specify a subnational equals to false. And looking at the plots, so it gives us the first order, the relatively quicker way to do a sanity check to see whether or not the results looks to make sense. So in this case, the shapes looks roughly similar to what we have seen in Kenya data from other locations. So this is probably fine. And we can examine that a little bit more closely by taking out the model components as well. So in this simple model, we only have a temporal random effects. So I will use this function called getDiag, or to get a diagnostic statistics. So here I'm specifying the field equals time, which just takes out the temporal components of the model. And if I run this line of codes, and you can see the random.time looks roughly like this. So you have a label variable which tells you which component this is. So remember, for a temporal model, we usually have a random walk with structured temporal random effects and also a ID random effect. So this first few rows here correspond to the random walk, and the lower, median, the upper values for the posterior median, and then the values for the posterior credible intervals. Okay. And since we're not fitting a period model, so remember, a period model is where we have the data that come to us with in terms of the periods, and then we want to fit yearly random effects so that we can impute what's at each particular year what the estimates are. Since we're not doing that because we're fitting the model on exactly every data points come to us as every year. So this is.yearly column doesn't contain much information. It's just all false in that case. Okay, so you can plot this random.time. So again, I'm just going to use the plot function internally built in the summer package. I'm using s.subnational equals to false because because this is not the estimates at the end, so it doesn't really have interpretation of each one correspond to one region. But I do want to separate them out into two different panels for the IID and the random walk parts. So I use this facet grid, or you can use facet wrap as well, to separate them out into two panels. And of course, I added titles and Y labels as well. So here, what you get is the posterior distribution, the marginal posterior summaries of those random effects. And you can see that IID term are relatively flat with some jiggling part in the middle, where the random walk took this shape that's our national that look exactly like our national estimates before. Okay. So when we go into subnational estimates, we will discuss a little bit more about other ways to extract information such as the spatial random effects, the space-time random effects, and how to visualize them as well. But for now, for the national model, this is the only random effects here that we can look at. Okay, so this is the first reason that we want to fit the national model in order to do some simple model fits, simple model checking before we go on fitting more complicated models and take much longer time. So another reason is that sometimes we might also want to benchmark our estimates to other published national results. So for example, here, what I will show you is to benchmark our results to the 2019 UN IGME estimates at the national level. So if you have worked in traumatology before, you probably have known that UN IGME published this national estimates of U5MR at each year, and they use much more data compared to our example here, which uses only one survey. So if we believe that is a higher quality information, we can benchmark our results, which basically means that we're going to calculate another bias adjustment factor and then benchmark our results to that. Okay, so the UN estimates again is provided in this in the summer package for Kenya. So it's in this Ken Data IGME 2019 objects. So you can look at, first of all, our outputs, out 0. And it has all the years. It goes from 1985 all the way to 2019. Of course, 2014 and NAs afterwards, because this is a direct estimates with no projection. And the UN object that we just created, if we take a quick look at this object. So this is the UN estimates for Kenya, starting from 1952 to all the way to 2008, I believe. Yes, all the way to 2008. So here we can calculate the ratio. So I'm not going to show you how exactly we come up with these numbers, but basically we go look at which rows corresponds to, again, 1985 to 2018 in our example. Right, so in this case, in the out 0 variable that we created, this is row 1 to 34, and in the UN IGME, this corresponds to 34 to 69. So if you print it out, you can very easily check those numbers. So you can calculate the ratio. And I created an object called adj.benchmark. You can take a look at it, which basically has two columns, one for the year and one for the adjustment ratio. Okay. So now we can further adjust our direct estimates by using this ratio. And again, we need to tell the function that's by which column that we want to merge these two. So in this particular case, we want to make the adjustments on each of the years and for all the regions. So we only need to merge these two data sets by this time equal to years, which corresponds to this column. So I'm going to run this line of codes. And again, it tells me how many estimates have been adjusted. Okay. So this is very similar to the HIV adjustment, except that now we're not making year province specific adjustments, we're just making yearly specific for all of the regions together. And you can make either of those work with this get adjusted function. Okay, so after fitting this model, we will, after adjusting the direct estimates, we can now fit the model on the subnational levels, and just to, again, as a check that we're doing something sensible, I'm just going to refit this model on the national level one more time using these adjusted estimates, and then compare the results to make sure that we're getting the results correctly. So those two lines of code were exactly like before, with the only difference that we're using the adjusted direct estimates here. Okay, so once this get smooth function finished running, we will have the smooth estimates, and here I will plot the smooth estimates from before, so this out 0, and the smooth estimates after adjustments, which is out 0 dot benchmark. Okay, so here we have finished running those two. So I will just run these two lines of codes. And I will add in the UN estimates, the ones that we were trying to benchmark on. And again, we need to specify what is the column that we want to plot, which in this case is a column that's called mean. And then I can specify the colors and the limits and other things. So now if we put these two plots side by side, you can see that here on the left-hand side where we have the national estimates before benchmarking, which have some noticeable differences, especially around here in the 1990s, and then some differences here as well, and then the 2014 afterwards, the trend is a little bit different. So now we can benchmark it by. So now if we work on the benchmark data sets, our national smooth estimates look to align with the UN estimates very nicely, and it ends up having the same temporal trend going forward into the future as well. So this is good. This shows that we are doing something reasonable. We haven't messed up the adjustment steps there. So now we can use this adjusted direct estimates, this saying I'm saving as direct here, to fit the subnational estimates, to fit the subnational models and get the estimates using these two lines of code, again using fit in law and get smoothed. Okay. So again, these two lines of code may take a couple minutes to run. So I have already run this before we get started. So I won't actually implement these two code chunks. I will just plot the readouts here. And again, I'm using just using the plot function within the summer package. And because now we are working with a lot of the regions, it might be more informative to look at the regions separately. So I wrapped the panels by the region. So each region gets its own small panel, which means that this plot function will take much longer time to run. Okay, here we go. So the plot is showing up here. Let me make it a little bit larger. So here I'm specifying is.subnational equals to false, which basically means in this plot function, again, you can check in the documents, but what it means is basically that for each of those panels, we're treating it as just one estimate instead of multiple. After we use this line of code to separate them out into different panels. So again, here, what you're looking at is a smooth direct estimates and their corresponding 95% credible intervals. And on the y-axis is the U5MR per 1,000 births. And all of those orange or yellow dots are the the direct estimates, direct subnational estimates that we get by using the data only for that particular year in that particular region. So you can see that in some of the places, like here and here, I can make it a little bit bigger. In some places where you don't have direct estimates going back in time, these temporal trends are basically fitted by imputing this. So it basically makes this trend goes back in time that looks like this, here and here, where you don't actually have any data. So again, as we discussed in the previous lecture, if we go into very fine resolutions in space and time, a lot of times we will end up with a situation where we don't have direct estimates because there are no deaths. And then it is questionable whether or not it's a good idea to smooth the direct estimates and obtain and take those as the smooth as the smooth estimates. So as later we will see that once we fit the binomial model, although in those periods there are no deaths, because there is still some data, we can calculate we'll get a little bit different behaviors in those places, and it's typically much more robust to our model specification as well. Okay, I'm gonna close that. So again, you can plot the maps using the functions that we have looked at before, the map plots and the hatch plots. And notice here that before I run those lines of code, it will take a really long time on this computer. So one thing here is I specify the bricks for the hatch from 0 to 900 with length 10. So basically 0 to 100, 100 to 200, up to 800 to 900. So this will make the hatching to be consistent when we look at different different plots and compare the results later. Okay, so now the plots have been run, and you can see that we have the estimates over time. Again, the U5MR, this is a smooth estimates. And you can see regions like here. If you remember earlier in the slides, I showed you the plot where the direct estimates really have no information about some of the regions here back in time. And this is one I just showed you in the time series plot where the estimates shoots up very high because of following the temporal trend going back in time. Okay. So if you're following the HTML file, you can work through each of those, work through how to make the hatching plots as well. But here, for the sake of time, I'm just not going to run these 2 lines of codes, which basically produces the plots you have seen in the lecture slides. Okay, so another topic before we move on to the next model is how do we grab the information, how do we grab the model components and see what components contribute to how much variation in our data, in our fitted model. So as I showed you earlier, that you can use getDiag function to get, for a national model, the temporal components. So you need to specify equals time. So you can do that for space and space-time as well. So fortunately, I haven't run this model here, so I won't be getting the results using this line of codes because I haven't run that fitting model to save time. So starting from now, let's switch to the HTML file so that we don't have to wait an extended amount of time to get everything to finish running and seeing the visualizations. But if you're following through the lecture at this point, this fitting of the smooth direct estimates is usually relatively fast. It will probably take a couple of minutes up to like 10, 20 minutes. But once we go into the later models, it can easily take hours to fit the model. And this is still ongoing project, and we'll probably improve our estimation techniques in the future, so it might take a little bit shorter time. But with that, let's move on to the HTML file, where we are still going to go look at the codes as well as the figures and outputs, but we're not going to type anything into RStudio. Okay, so we have just switched from RStudio to the HTML file, which you are seeing on the website. And this, because it took a relatively long time to fit those models, it's much easier for us to look at results in this way. So let's jump directly into the smooth direct estimates, like we just obtained. And those are some of the figures you have seen before for the national model. And this is a hatching figure that I showed you earlier in the lecture PDF slides. And this is the comparison I was talking about. It's for a lot of the places, because going back in time, there's no data. The smooth direct estimates are determined are influenced strongly by your prior setup and the temporal trend you learned in the model. Okay. So picking up from where we left just now, let's look at the diagnostics. So if you run these 3 lines of code, it will give you respectively the posterior summaries of the temporal, spatial, and spatial temporal random effects. So again, this is the command that's similar to what we have looked at before. I just plot this random.time, and I separate them out by their label, which correspond to the IID's temporal random effects, as well as the random walk temporal effects. And you can see that in this case, the random walk looks roughly like a downward trend in this case, with more uncertainty as we go into the projection area, which is as what we expect. Okay. So we can also look at the spatial random effects. So remember, this is the BYM model, where in the lecture series we talk about BYM2 model, which was fitted here. So here we're using this map function to plot the random effects again on the map. So we have the BSEG, or the ICAR part of this, or the structure part of the random effects on the left, and then the total effect. So that's the sum of the ICAR plus the IID spatial random effects showing up here. And you can see that there are again quite some variations across space, and on the logit scale, they go from about -1 to 2, or -1 to 1 in the total sum here. Okay. Okay. So we can also plot the space-time interaction effects. So what this does is that it tells you from the so imagine space and time are 2 dimensions. So what this tells you is that how much or what is the shape of the deviation from this temporal trend, this general trend you see in the first random walk plots, and the spatial trends, which is just that map that we have just seen. So apart from those 2 main effects, in each of the region over time, they deviate a little bit from those 2 main effects, and they are captured basically by these interaction effects. And again, when we fit the model, we specify the type 4 interaction, which makes this interaction smooth over both space and time. So you can see this relatively smooth curves, or these smooth points over time for each of those regions. Okay. And of course, if here something seems off, some regions that should not deviate from the overall trend by a lot. For example, in this particular area, there is this very big deviation from the trends, and if you're analyzing your own data, you might want to go into your data to see whether or not this is something that makes sense, or whether or not it is a data issue, a data processing issue, or if the model mistakenly estimated something that's not there. Okay. So we might want to use those diagnostics plots to examine whether or not we're doing the right thing. And it will typically be more informative than just looking at the estimates, because sometimes when the estimates goes down, they might be relatively flat or have a relatively steep trend, and then it will kind of mask out some of the variations that are captured in those parts. Okay, so with that, I'm going to conclude this part of the lecture and move on to the next model, which is the model-based estimates, or the cluster level modeling. So as we discussed in the lecture, this is very different from both the direct estimates and the smooth direct estimates, because here we're directly modeling the hazards for the 6 age groups, or you can specify your own age groups as well. So I won't go into the details. The notation here is probably a little bit different from the lecture as well. So if you're interested in learning a little bit more about these models, you should definitely check out the Wakefield et al. 2018 paper on SMMR. But here I'm just going to quickly show you, go through some of the details. So we're working on the hazards level, and we want to get stratum-specific estimates of the hazards, and then we want to use those stratum-specific hazards to combine them and piece together the U5MR at the end. And we're going to use the beta binomial distribution on each of the clusters. And one thing that's a little bit different from before, that when we want to do a bias adjustments in the smooth direct estimates, what you need to do is basically to adjust your direct estimates so that you're smoothing the right version, or the adjusted version of the direct estimates. In the cluster level model here, basically what we're assuming that we're using this log bias to be a approximated offset for our logits of the U5MR, or the logits of the hazards. So there are a lot more details about this model in the Wakefield et al. 2018 paper, so you can go in there and read a little bit more. But from a implementation point of view, what we need to do is basically in fitting the model, if we want to do bias adjustments, we need to specify a bias data set, a bias adjustment ratio data sets, as we will see later. Okay. So here we're just repeating some of the steps in case for anyone who wants to pick up from here. We're directly using the birth records data from the DHS data websites, and I will repeat the data processing steps up here that turns these data sets into a person month format in these first 3 lines of codes. And then one thing a little bit different in the cluster level modeling is that we're not only going to be extracting the direct estimates. In fact, we don't actually need the direct estimates, but we need to calculate for each region and each year a binomial outcome. So how many total person months in that particular year in the region, and how many deaths happened in a particular year in the region. And then we want to do this for each of the strata, and then for each of the age groups. And that's what we do with this getCounts function. We basically specify the data, specify the variable that we're interested in, which is y, that we created in this line of code. And then we want to calculate the counts by age, strata, as I said, cluster, and then years. And then, of course, since there are no data after 2014, I will just ignore those years so that we don't impute all the possible combinations of year, age, strata, and clusters in those projection years. And if you run this line of codes, you get the outcome, which basically looks like this. So again, you have the age group, strata, cluster, year, and corresponding to the combination of those things, we have the y, which is the number of deaths in this context, and then the total number of prison months. So now we have arranged our data into a form that we can fit the binomial model on. So again, we will use the GPS data set to merge the region as well as the province back into these data sets. So we're going to use, so basically finding out for each cluster which region, which province it corresponds to. Okay, so that's this step. Then again, we're extracting the adjustment factors, just like before. And again, the first thing that we want to do as, again, both as a model checking step and as well as a benchmarking step if we have national estimates. And then, again, in this case, we'll be comparing to the UN IGME estimates. So what we will do, we'll come back to the formulas in minutes, but what we'll do is we create another variable called outcome_national, which is basically the outcome that we just created, the binomial data format we just created. And here I specify the strata to be the region and the strata. So remember that if we're working with a subnational model, the strata, what we mean by strata in the codes is that within each region, what is the variable that's stratified within that region. But if we work with a national model, then we need the strata to be the actual strata, which is the region crossed with the urban-rural strata that we're using in this particular problem. So I'm going to create a new variable called strata in this national data sets. And I will use this function called fit_in_lat2 to fit this binomial or cluster level model. And you can see that there are some very similar arguments as before. We specify the data, we specify AMAT, geo to be null, we specify the years. But this is a little bit different here that we're using the beta binomial family. So here we specify what model we want to use for the cluster level modeling. And then we in this particular case, we put in the adjustment factor using this bias.adj, which corresponds to the HIV adjustment factors we talked about before. And this is adjusted by year and province. That's what our data tells us. And then here, this is one thing that we haven't seen before. So what this argument does is basically says that because now instead of working on smoothing the direct estimates, we're smoothing directly on the hazards. So we have to make the decision that for each of the 6 age bands, do we want them to share the same temporal trends, or do we want them to have different ones? So this arguments here, this specification here, basically says that we want, for those 6 age bands, we want the first, second to each have its own distinct temporal trends, and then we want the rest of them to have the same, or the third temporal trends. So we're basically going to fit a model with 3 random walk effects, as we will later see when we extract the post-series as well. Okay, so if you fit this model, this will take a relatively longer time to fit because it's more complicated. And then we want to get the estimates. So in order to get the estimates, again, already discussing the lecture, that we need not only the estimates from our model itself, we also need the population proportion by each of the strata, right? Because what the model gives us is a region year stratum specific estimates, and then we want to aggregate them up to region years. We need the population the population proportion basically at each year and each region and for each strata. But when we feed the national model, we only need because there's no space around, so we basically just need the proportion by proportion of each of the strata by time. Okay, so we're going to calculate that using these few lines of codes, which if you look at if you implementing this in real time, you can check out what the data frame looks like. But basically, this calculates the urban-rural proportion for the entire country. Okay. So now we're going to use the get smooth function. And I'm going to take the fitted value, the years, and I'm going to use this function, this argument called weight.strata, which is the proportion at the national level that we just created. And then use this get smooth function to get the actual posterior estimates. And here we also have an argument that specifies how many posterior draws that we can get, that we want to take in order to calculate the estimates. So of course, the more posterior draws you want to specify will take a longer time to run, and the fewer draws you make, the results will be less stable. So just as an illustration, I'm just going to take 1,000 draws here, which should be relatively fast. And then you can get the estimates. So unfortunately, I haven't plotted the estimates here, but we will show you in a few minutes, actually. Actually, here you can see that this is, again, a little bit of a preview of what's going to come. So that this is estimates before benchmarking. It will look very similar to the one before in the smooth strata estimates, and the orange dots are the UN estimates, which we'll be benchmarking against in a minute. Okay, so now going back, remember that figure where you have two different trends. If we want to benchmark our estimates to the UN estimates, what you need to do is basically to recalculate your adjustment factor. So remember, before, our adjustment factor are based only for the HIV estimates. We're going to use this simple formula that basically says that we're going to change our bias adjustment formula by, again, multiplying this additional term, which is our estimates that we just calculated, divided by the UN estimates. So it's basically a compound of those two bias adjustment ratios. And we'll use that as the new adjustment factors. And this few lines of code is basically calculating those benchmarking adjustment ratios by very, very easily merging those two data sets and just calculate this new ratio and multiply into the original ones. Okay? And you can visually compare the adjustment ratios here with this few lines of code, which I'm not going into the details. So on the left-hand side here are the HIV adjustment ratios for each of the provinces over time, and you see that as we looked at before, that our estimates is a little bit lower than the ones from the UN ICME, so that the new adjustment ratios is a little bit smaller after taking into account that step of the benchmark. Okay, so again, once you have done that, you can use the few lines of codes. Again, very similar to before, except we're using this new benchmark version of the adjustment ratios. And you can plot the results similarly as before. So here we're looking at the adjusted version of the national estimates, which is very smooth and similar to what the UN does, what the UN estimates look like. Okay, so again, you don't have to do this step. This is just for the model checking. But once you have the new adjustment factors, you can fit the subnational model, again using the function called fit in LA2. And I specify it to be beta binomial, and the rest of the arguments are just exactly as before, with the only new thing is that I'm specifying which space-time interaction formula, which space-time interaction random effects I want to use. In this case, I use the most complicated type 4 interactions. Again, gives you a smooth deviation from the main trends. And then you can use the plot function once you fit that model, which will take, if you have a lot of regions, it will take hours or probably even longer than that to fit the model. But once you're done, you can again use the plot function. And this gives you the subnational estimates of U5MR over time for each of the 47 regions. And the functions here are exactly the same as before. Because we're plotting a lot of things here, so I set the plot.ci to be false, so only the posterior medians are plotted on these figures. And you can go find those regions directly here. And of course, just like before, we can calculate we can plot them into different panels as well using this line of codes. Again, you have seen this repeatedly. I'm just adding this one component that separates things into different panels. Over here. And you can plot them on a map using the map plots. So one thing you might have noticed by this part is that the estimates you get at the end, we have, because there is a weighting stage in the middle, so at the end of the day, what summer output gives you is first of all a stratum-specific set of estimates, and then there's overall estimates which takes your input weights and combine them together to get the overall U5MR. So that's why here I'm just plotting for the overall estimates and subsetting the data so that I'm only plotting a few years, so it's easier to see here. And this is the results. And just like before, you can use hedge plots to plot the hatchings as well. Okay. So by this point, we have already looked at direct estimates, smooth direct estimates, and then cluster level modeling, where we gives you, which takes a lot more time, but gives you this set of estimates at the end. So before we formally compare those three, so just want again quickly show you some of the additional diagnostics. So again, as said here, you can always use summary to summarize this fitted object directly. If you're familiar with inla syntax, the results might make a lot of sense to you. But if you're not familiar with fitting models in inla or those diagnostic statistics, one thing you can always do is by just plotting the posterior summary distributions for each of those random effects. So again, here I'm grabbing the time components here for the for this binomial model. And remember that we have fitted the model with 3 different random walks, one for the first age group, 0 to 1, another for age group 1 to 11, and then for age group 12 to 60. Okay. So that's why there are a few lines of codes. So if you do this get diag, you get the ID, you get basically 7 sets of the estimates that corresponds to the 6 age groups and the ID shocks. So I'm renaming it a little bit, and I'm because I know that the age groups, the last 4 age groups share the same random effect, I'm just going to take one of them and plot it here. Okay, so here you can see that this is the spatial random effects or the temporal trends for those age groups. So this is first, second, and third. The second and third looks quite similar, but the first one, which corresponds to neonatal mortality, have a much flat curve across the time. So this indicates that the habits of dying in the first months have stayed relatively flat over time compared to the other age groups. And then, of course, we have some IID shocks over time as well that's showing up here, which is on a much smaller scale than the other temporal components. Okay, so again, you can plot the space-time interactions. So here, this is the same codes as we have seen before, and we can also plot them on the maps over time as well, which will be also interesting to look at if you are interested in a particular period of time and see how the estimates deviates from their main trends. Okay, so finally, before we wrap up this example, I want to just compare those three set of estimates that we have calculated today. So we have the direct estimates, the smooth direct estimates, and the model-based or the binomial or the cluster level model estimates. Right? So those corresponding estimates have been saved if you follow along the script in the out0.sub, out1.sub $ overall, and then the direct, which is just the direct estimates that we have calculated. So here I'm basically combining those and taking out relevant portions of those estimates, so the region here, median, or for the direct estimates, the means, and then the upper and lower confidence of credible intervals. And I'm giving them names and put them together into the same data sets. They're called readouts. And here, there are a lot of things on this screen, but here basically what I'm doing is I'm plotting this readouts data frame. So I'm using ggplot. So the x-axis here is year, so from 1985 to 2019, and the y-axis is estimates, which are the three estimates. And I use color to indicate the type of the estimates. So if you go down here, you can see that, again, there are too many things on the screen, so it's really hard to see, but you can see the blue here corresponds to directs, orange corresponds to smooth directs, and the red corresponds to the binomial model. Okay, and then I added the error bars and put them into small panels where each panel corresponds to one region, and put the legend to the bottom. So the first thing you might notice here that there are quite a lot of agreement between the orange and the red, and they both have much smaller credible interval, much smaller uncertainty than the direct estimates, which are the blue curves, the blue error bars here and there. But the two smooth estimates, the smooth direct estimates and the binomial estimates, the cluster level model estimates, also differ a lot in some situations. So if we zoom in, this is as far as I can go. So in some places, like here and here, where you can see that there are no direct estimates because there are no deaths, so you cannot you cannot estimate the prevalence without any outcome. So in those cases, the orange curve or the orange bars, of course, could take a different shape or a different trend than the red ones, because the orange here, the smooth direct estimates only makes use of the information from the direct estimates, and if you don't have them, again, I have said this repeatedly in this lecture, that it might give you suspicious results depending on your prior choices, while the binomial model is much more robust to that because you can actually use the data. You can actually use the data even though there are no deaths, because you can still fit the binomial model with some person months, but no deaths in a particular time or area. But in general, as you can see here, that both those smooth directs and the binomial, the cluster level model, follows roughly along the direct estimates in a smoother way, like here and here, but with much smaller uncertainties and pretty good agreements. So that is a good thing for us as a model checking step. Okay, so here again, this is the similar setup. It's just visualizing in a slightly different way, where I take out a few selected years. So this is 1985, 1995, et cetera, et cetera. Last one is 2014. And I have sorted the estimates. I have sorted the counties so that they have from big to small estimates using the binomial model. And you can see that again, that the blue error bars are much wider. The direct estimates have much larger uncertainty than red and orange. And red and orange, or the two smooth models, are quite similar in most of the places, especially in the places where we have a relatively good direct estimates. So that all makes sense as well. Okay. And finally, again, in this last few figures, I didn't go into a lot of the details in the visualization, but I believe at this point you have already been familiar with some of the setup of the ggplot and the arguments how to do that. So it's relatively straightforward to understand what's going on here. So I will skip those details. But the last figure I'm showing you here is comparing those direct, smooth direct, and binomial or the cluster level model by just putting them together and see how much they agree with each other. And you can see that here this is direct estimates, this is smooth direct estimates. There are quite a lot of agreement with a little bit of smoothing, but when our smooth estimates were put down a little bit in those points where we probably have a very large direct estimate, which could be due to small sample sizes or very sparse data in those particular time and region. And we see a little bit more smoothing when we compare smooth directs and the binomial model as well. But the overall, the general trend is very similar, which indicates that both models perform relatively well for the majority of the data in our case. So again, as we have repeatedly echoed in this course, that as we go down into finer spatial and temporal resolutions, smooth direct estimates might not be the best model to fit because it relies on the direct estimates, which will have much higher uncertainty and very little precision, and probably sometimes, as we have seen, it cannot be calculated. So in fact, for most of the DHS surveys, if the survey is powered to, say, admin 1 level, and if you go to admin 2 level, you have a lot of problems like that where we have sparse data, or no deaths in particular region at time. This particular example that we're looking at, Kenya 2014 DHS, was actually powered to the level of the counties, which allows us to get most of the direct estimates, those blue error bars here in this figure, so that we can compare those methods. But in general, we will usually suggest that fitting the direct estimates and the smooth direct estimates only to the level where the survey is powered to. So for a lot of the surveys, that will be just at admin 1 level. And then the binomial model can be used to further go down to finer spatial resolution into admin 2, and also potentially with finer temporal resolution as well, like what we're doing here is estimating the yearly model. So here I think we have a complete recipe for at this point by using to use the summer package to fit the model at different levels and have different model components. So with that, I will wrap up this particular this last lecture. And again, this is still ongoing work, so there are likely to be new publications and new methods and new implementations in the summer package to do some of the new stuff in the future as well. So stay tuned. There's the website where we have hosted all of the materials that we discussed in this lecture series online, and there will be new stuff in the future as well. Okay, so with that, I will conclude this session using R to fit subnational estimates. Thank you.